figure it out here. All right, so this is the next one. So what you should have gotten is this, basically. We saw with sodium hydroxide, where? Well, basically it's going to be sodium hydroxide solid here. It's exothermic, so we're losing. And we're going to form sodium hydroxide aqueous here. Now, what is our system? Is our system an object, or is our system a reaction or process? It's a reaction or process. It's the dissolution process. And so this is going to be at whatever temperature we call it. We'll just call it T cold for room temperature. T cold, because something's going to get hot, right? And so what gets hot? Well, all that heat's going to go into the surroundings. So what is the surroundings? Now, this is where people have a lot of difficulty with the surroundings. And so what we're doing is we're going to take not 1 mole. 1 mole is too much. We're going to take x.xx grams of sodium hydroxide. Luckily, you don't have to weigh it because it's a pain to weigh. And so we have x.xx grams of sodium hydroxide, which is some number of moles of sodium hydroxide. And the sodium hydroxide is still there, so, you know, whatever it is. But what will our surroundings be? Now, what we're going to do is we're going to dump it in water. So we have to have a certain fixed amount of water in there. And how much water are we going to put in our cup? If we put too little water, you know, the temperature is going to get quite hot. It's going to be hard to mix. So actually, we're going to put in 50 milliliters of water. And so the way this experiment's going to work is we're going to have 50 mils of water in here, H2O liquid, and then we're going to pour our solid sodium hydroxide into this water. And so what should we do? Well, we need to monitor the temperature of the water. And so in this case, we aren't going to monitor the temperature of the sodium hydroxide because I guess we could put a thermocouple on top of it, but we aren't. It's going to just be room temperature. But we'll monitor the cold water because the cold water is likely to be colder than room temperature. So we'll monitor for how many minutes? Like 5 minutes, right? And then at minute 6 or minute 5, actually it should be in this notebook. Let's see if it's in this person's notebook. Let's see. 1, 2, 3, 4, 5, 6. At minute 6, we mix it. Actually, it's not totally clear. Let me see. What else is notebook here? I collect the notebooks at the end of the semester, but a lot of people don't pick it up at the end. It isn't much worth. The lab notebook. I just check it off. See if you have your observations in there. The final check of your notebook. Oh, that notebook's pretty good. And so at minute 6, it's mixed. But do you think that solid sodium hydroxide dissolves in 1 instant of time? No. What happens is the sodium hydroxide takes some time to dissolve and you're scraping it off. You bring a watch plate, stock room, and she'll weigh some out onto your watch plate. And then you scrape it off your watch plate into there. Sodium hydroxide is also known as drain cleaner or lye. Now, solid sodium hydroxide is hazardous to your health, although you can buy it in the supermarket. You'll know if you touched it because your fingers will become extremely slippery, right, as it destroys. I think it destroys your cell walls or whatever. But it's an extreme eye hazard, especially solid. You know, we've been using dilute sodium hydroxide. Okay, dilute. It's really dilute, 0.1 molar. You know, but this stuff is pure sodium hydroxide. And quite hazardous. And so at minute 6, it's not completely mixed, so we get the same weird results. So at minute 6, you know, probably at minute 6 when you're mixing this data point is still reading, you know, really low temperature. And so this is worthless data here. And then you mix it and the temperature jumps up, but you know, we have this pattern once again. And this pattern once again is this, you know, something like this. Do you expect it to warm up, cool down, and then warm up again? No, this is because of, what did we call those? Why do we see a pattern like this or a random pattern like this? Somebody remind me the word we use for that. It's because of heat gradients or incomplete mixing. So all these initial points are not as significant. So this is why we collect data out here, because once everything's thoroughly mixed, we should see a smooth cooling curve according to Newton's law of cooling. Right? And then what we're going to do is we're going to back extrapolate this to the mixed temperature. The mixed temperature we don't actually record. The mixed temperature we get from the graph. And so this is T mix or T hot. And so what are we dumping the heat into? What's our surroundings now? And so this is our system. Our surroundings is going to be like this. Make sure I have enough time to finish all this. Our surroundings will be, you tell me what our surroundings are. Well, it's going to be the calorimeter. Is that it? The surroundings will be whatever's left over after the dissolution. After you completely dissolve the sodium hydroxide, does the system exist anymore? No. The system, has a finite lifetime. Any reaction or any process is going to have a finite lifetime. Once that lifetime's done, the system's gone. All that remains from the system is the heat that got dumped, right, into the surroundings. And so this is weird to think about, but what is our surroundings? Our surroundings is this. It's going to be 50x.xx grams of solution plus calorimeter at T cold. And this is going to warm up by all this heat being dumped into it to 50x.xx grams of solution at plus calorimeter at T mix. And so what's left over, let's say, it says to use 2 grams or so. So if I use 2 grams of sodium hydroxide, I'm going to have 52 grams of sodium hydroxide solution left over that's going to warm up from the heat, right, that got dumped in there. Plus the calorimeter. The calorimeter is a coffee cup apparatus. And so this will be my surrounding. So this is my system here, and this is going to go into the surroundings, right? Q, the surroundings is here. All right, so let's set this up. Oops, I didn't want to erase that because the system is a reactional process. What is Q of my system? Haven't started. Well, I introduced this early, so you have more time to memorize it. But Q of the system is equal to the amount times delta H, or the amount times delta U. Delta H is under what conditions? Constant pressure. Delta U is under, okay, was there a volume? Did the volume, if I did this in a bomb, would I have to worry about a pressure explosion? No, because really no change in volume, right? Everything's still there. The 50 mils of water, the sodium hydroxide, all that's going to take up volume, right? And so I didn't see any gases being generated or gases being consumed. And so in this case, they're equal. In this case. In other cases, they are unequal. Right? But in this case, they're equal. Because it doesn't matter if you did it in a bomb or you did it in a coffee cup, you would have gotten the same result. You would have gotten the same amount of heat. Okay? Whereas the earlier example I showed, with this, they would have, no, it's going to be a different amount of heat. To blow up the balloon. What was that earlier? KClO3? They're been totally different. Delta U and delta H are not the same. I haven't defined delta H yet, but everybody knows delta H, don't you? Tell me the definition of delta H. Change in heat. What's the definition of delta U? Well, okay. Then you don't really know the definition of delta H, because it's not just a change in heat. And so we have to have a more precise definition than that. We'll talk about delta H later, but not now. We're just trying to drill this in. And so delta H and delta U are the same thing in this case, because constant pressure, constant volume doesn't matter. All right, so what we have here is Q of the system is going to equal Q of what we call dissolution. It means dissolving sodium hydroxide dissolution, which is going to equal the amount times delta H. We're going to just use delta H because we're doing this under constant pressure. But you would have to know this later, as you go on, and probably in the middle part of this chapter, you're going to start talking about delta U and delta H. Okay, all that heat is being dumped into the surroundings, so this is going to equal minus Q of the surroundings. Okay, what is the surroundings? What do the surroundings consist of? The surroundings consist of the amount of solution times C of the solution times delta T of the solution plus the calorimeter. The calorimeter, how many calorimeters do we have? One. And so it's going to be C of the calorimeter times delta T of the calorimeter. Delta T of the calorimeter and delta T of the solution are the exact same thing because they're at the same temperatures. In other words, they're in thermal equilibrium, thermal contact. And so these two delta T's are the same. Now, unfortunately, I have a problem here. And the problem is I know the amount of solution, 50x. Point XX, depending on how much the stockroom gives you. They're going to tell you what X point XX is. But I don't know C. I don't know the heat capacity or the specific heat of a sodium hydroxide solution. And so we're going to make an assumption. What assumption are we going to make? Well, one, is it a concentrated sodium hydroxide or dilute sodium hydroxide? It's pretty dilute. And so if it's fairly dilute, then the heat capacity of the specific heat should be somewhat close to water. And so what we're going to do is we're going to assume that the heat capacity of sodium hydroxide, AQ, is about equal to the heat capacity of H2O liquid. The heat capacity of H2O liquid, everybody should have that memorized, 4.18 joules per gram degrees C. And this is a reasonable assumption. It's not going to lead to a huge error, but it is an error, nonetheless. It's going to we'll just do that. And then you know what we're going to solve for? We're going to solve for, Q, and then we're going to solve for delta H. And so what we're going to get is delta H of dissolution. Delta H of dissolution is just that Q divided by, it's just Q divided by the amount. Right? Q of the system, or we'll say Q of dissolution divided by the amount. We're going to solve for delta H in 2 units. We're going to solve for joules per gram or kilojoules per gram, and then kilojoules per mole, depending on if we want the amount in grams or if we want the amount in moles. I went out of order, sorry. This is number 3. Number 2, but again, you know what? It doesn't matter what order you do these in, really. But number 2 is we're going to do this. We're going to take 50.0 mils of sodium hydroxide, AQ. It's concentration. Did they write the concentration? You did not write the concentration. That's not a good observation. Plus 50.0 mils of HCl. This is not going to be a stoichiometric mixture. You know what a stoichiometric mixture means? Just the right amounts of everything. This is going to be excess reagent, limiting reagent. Do you know what our excess reagent is going to be?
HCl.
I'm pretty sure it's HCl. Yeah, I'm sure this has got to be HCl. It's got to be excess reagent. And so the amount of reaction is going to depend on how many moles of sodium hydroxide we react, not on how many moles of HCl, because some of it's going to stay unreacted. When we do an acid-base neutralization, what do? We add acid or add base? Well, normally when you do titration, you add base, right? But according to our safety rule says to add the acid. But you know what? Both of these are so dilute, it's not that big of a deal. You know, it's just when you're dealing with concentrated things that's a big deal. And so which one do you want to call our system? Which one do you want to call our surroundings? Well, what is our system? What are our surroundings? I'll tell you what our system is. Our system is HCl plus sodium hydroxide yields sodium chloride plus H2O liquid plus energy. You know, this plus energy, this means delta H is less than 0, which we'll talk about later, but this is exothermic. Our system is this. What is our system? What's our system here? Our system's a reaction. And so our system's going to look like this. We have HCl plus sodium hydroxide, this. This is going to drop down to sodium chloride plus H2O liquid. What's T final? What's T initial? Here. T cold, and T final is going to be? No. No. It's not an object. It's a reaction. What's T final? T cold. Remember, the temperature does not change. The kinetic energy does not change. The only change is potential energy. So what gets hot? The surroundings. What are the surroundings? Not water and calorimeter. The surroundings are, there is water and calorimeter, but you're missing something. You're missing sodium chloride. Our surroundings is going to be sodium chloride AQ. What's left over? What's left over is where the heat's going to be dumped. Our system doesn't live forever. The product does, right? Sodium chloride. And so the object now is going to be sodium chloride aqueous plus calorimeter at T cold. And this is going to warm up to sodium chloride plus calorimeter at T hot. And so this is an object. Our surroundings is an object. Our system is a reaction. So what we're going to do is we're going to call one of these the calorimeter. We have 2 coffee cups. Which one do you want to call the calorimeter? Well, it depends. Do you want to pour the acid into the base or the base into the acid? Well, I don't know what the procedure says because I don't have the procedure and they didn't write it down here. Let me see if they wrote it down. Oh, they poured the acid into the base, so that's probably the procedure there. And so this is good. This person has decent observations. I can follow it. And so what we're going to do is we're going to call the base coffee cup the calorimeter. And the acid coffee cup is going to be ignored. The base is the limiting reagent, so it makes sense. If we don't get all of our HCl in there, no big deal because that's excess reagent, right? And so we have excess HCl. And so we're going to have HCl left over here too. And so it's not just sodium chloride, it's HCl, AQ, plus sodium chloride AQ, plus calorimeter. And that is going to be our product mixture. And so this is going to be our calorimeter here. What are we going to do? We're going to monitor the temperature. We're going to monitor the temperature of the sodium hydroxide. But since we have two thermocouples, we can also monitor the temperature of the HCl. Hopefully they're the same temperature. They should be. And so we're going to monitor both. And so the temperature of the HCl, the temperature of the sodium hydroxide, they might not be exactly the same, but they better be very close. They might not be exactly the same because it depends on the thermometers, the thermocouples. If you take two of those mercuries, are they measuring the exact same temperature in the exact same solution? No, because there's manufacturing errors. There's certain precision to that. And then all of a sudden at minute 6, the temperature is going to pop up and fluctuate. But we're going to wait until the temperature stabilizes and we get a nice cooling trend so we can figure out what the temperature should have been at the time of mixing. Right? And so this will be T mix here. This is T mix, this is T cold. Or you could call it T hot, T cold, but I don't call it hot because it's not an object, a hot object in this case, but it doesn't really matter. And so you pop the lid off here, pour this in here, some heat, neutralization is going to result in warming up the solution. And so let's look at the system. The Q of the system is Q of the neutralization, right? Acid-base neutral. What kind of reaction is this? This is a metathesis or an acid-base reaction. And so it's just Q of the reaction. In fact, let me just rewrite this. Q of the reaction. Okay, Q of the reaction is equal to what? Well, let me ask you this. Is this constant pressure or constant volume system? It's constant pressure. We're not doing it in a bomb. If we did this in a bomb, would we have generated excess pressure? Or would we have consumed pressure and made a vacuum if we did this in a bomb? So let's say you had some pan portals in a bomb and you're able to pour the HCl into the sodium hydroxide beaker. Are you going to be generating pressure or consuming gas pressure so that you need a bomb to withstand those pressure differences? Yes or no? No. I mean, we start off with 100 milliliters total. How many milliliters of product solution do you think we're going to end up with? 50 milliliters plus 50 milliliters is going to make 100 milliliters, right? Or close to it. Sometimes volumes aren't totally additive. Sometimes you take 50 milliliters and 50 milliliters and you end up with a little more or a little less depending on how the molecules pack together, right? But even if we have that, those changes are very small and negligible. And so in this case, we start off with 100, we end up with 100. Is that going to generate a huge amount of pressure? No, actually there's no volume change, right? The total volume initial is equal to the total volume final under constant pressure conditions. You know what that means? That means delta H and delta U are the same thing. And so Q of the reaction here is going to equal the amount times delta H of reaction. And in this particular case, it equals the amount times delta U of reaction. Because they're the same thing. Okay? But of course, we need to put an asterisk here because this is not always true. But in this case, it is true. Okay, this is going to equal minus Q of the surroundings. So this is minus Q of the surroundings. What are the surroundings? Well, the surroundings are going to consist of the HCl sodium chloride solution. How much HCl sodium chloride solution do I have? Well, I'm going to have 100 mils, right? 5.0 mils, assuming the volumes are additive. Okay. Times C times delta T plus the calorimeter. And so the amount of calorimeter is 1 times C of the calorimeter times delta T. But, you know, unfortunately the problem is I don't have the specific heat. And in fact, I don't even have the density of this. So I need to make two assumptions. What two assumptions do I need to make? One, in order to do this, I need to assume that the density of the product solution is close to the density of pure water. This assumption is reasonable if it's fairly dilute, which it is. It's going to be pretty dilute. This is only like 0.1 molar. And what's the other assumption I'm going to make? That the specific heat of the product solution, or the heat capacity of the product solution, is about equal to the heat capacity of pure water. And then I can solve this. Well, what am I going to solve for? I'm going to solve for Q of the reaction. Right? You're going to solve for three things if you look at the report sheet. You're going to solve for Q of the reaction, delta H of the reaction in units of, I think, joules per gram, and delta H of reaction in units of kilojoules per mole. And so here we're solving for Q of the reaction, and then if we want delta H, we just divide it by the amount, either the amount in grams or the amount in... Actually, no, are we doing this one? We aren't doing kilojoules, we aren't doing the grams. The sodium hydroxide one, we're doing the grams because we're adding x.xx grams. This one we aren't. And so we're just solving for delta H in kilojoules per mole, or Q of the reaction in joules, or actually both. And so this is another 15-minute experiment. So that's 15, 15, 15 of data collection time. And then maybe, you know, 5-10 minutes for setup, maybe longer. Okay, the next one is our last one. And so we're going to do 1, 2, 3, 4 15-minute experiments. An hour's worth, plus all that setup. And so hopefully in 2.5 hours we can finish it if the drill is only 30 minutes long. I'm going to help you set up the LabQuest. The LabQuest is easy to set up though. Okay, the last one is going to be this. The last reaction is going to be solid sodium hydroxide plus HCl8Q. Okay, what's this going to yield? Well, sodium hydroxide is a soluble salt, right? We're going to form sodium chloride plus water. What do you think is going to be in excess? Well, we're going to have excess HCl. Right? And so again, we're going to have x.xx. You know, the stockroom is going to wait out for you, because this stuff is hydroscopic. What does hydroscopic mean? In fact, this is so hydroscopic, they call it deliquescent. Have you heard the word deliquescent before? Sodium hydroxide is not used as a primary standard. What is the primary standard? The primary standard. Deliquescent, hydroscopic. Those are words from the titration lab. How do you remember those? I'll leave it up to you. But what are we going to call the system now? Set up the system for me. Well, let's set up what do we call this diagram? Energy level diagram. You won't believe how many times I've asked for an energy level diagram and people come up to me, what is an energy level diagram? Every single exam somebody asks me that. What is an energy level diagram? Well, this is an energy level diagram. Energy level diagram is going to plot out some arbitrary energies here. I don't know what they are, the numbers. But all we know is this is higher in energy, this is lower in energy. These are energy states, we call them. In thermo, we work with state functions. And state functions, we only care about what? In thermo, we work with state functions. The reason I'm trying to repeat these, at least the thermo terms, as much as possible, because next week, the test. State functions we worry about the initial and the final. We do not worry about something called the path. There are certain path-dependent functions, and then there are state functions. A path-dependent function is going to change, you know. A state function never changes. The path-dependent function is going to change depending on the path. But anyway, what's higher? This is higher in energy. What kind of energy is this higher in? Tell me. Then the products. The products are going to be lower in energy. And so you would say the reactants are higher in energy in both kinetic energy and potential energy. True or false? False. Right, just potential energy. Because this is going to be at T cold, this is going to be at T cold. And so there's going to be a big drop in potential energy, and it's going to be dumped out as heat. So this is a Q of the system. What is Q of the system equal to? Here. So anyway, we're going to have x.xx grams of sodium hydroxide plus 50 mils of this, and we're going to end up with how much product solution? This is going to be HCl, excess, plus sodium chloride plus water. How much product solution do we end up with? We end up with 50x.xx grams here. This, but this one we don't. This is x.xx grams of this. We aren't dealing with full moles here. And some amount of excess HCl, I don't know what it is. What's Q of the system equal to? Well, this is a reaction or process, so Q of the system is equal to Q of reaction, which is equal to what? Amount times, are we doing this under constant pressure or constant volume? Constant pressure, so amount times delta H. But if we did this in a bomb, would it have changed anything? No. And so in this case, it's equal to the amount times delta U. Thermal, we have to keep all these relationships in order so that we can do our calculations. Where's all this heat being dumped to? The surroundings. And so what do the surroundings consist of? Now, you know, repeated this a number of times, so now you tell me what the surroundings are in an energy level diagram. And so the heat's going to go into the surroundings. What are the surroundings? Well, I don't have time, unfortunately. I got to keep moving because I need to discuss some other stuff as well. The surroundings are going to be the HCl, sodium chloride, and water. What we call the product solution. Product solution at T cold. And the product solution is an object. This object is going to warm up, right? So we're going to get HCl, sodium chloride, and H2O liquid at T hot, or T mix. So Q of the surroundings is equal to what? It's equal to the amount times C times delta T for the object. The object is a product solution. So the amount of product solution is 50x.xx grams. C of the product solution. Do we know it? Unfortunately, we don't know it. Delta T we know because we're going to do the same thing. We're going to monitor the T cold, and then we're going to figure out T mix by back extrapolating it, by graphing it. right? And so what are we going to assume here? We assume that C of the product solution is about equal to C of H2O liquid. Okay. All right, so then we put it together. Q of the system using the first law of thermodynamics. What does the first law of thermodynamics say? It says that Q of the system is equal to minus Q of the surroundings. And so we get the amount times delta H is equal to minus, okay, amount times C times delta T plus C of the calorimeter times delta T. And then we solve for delta H and we solve for Q of the reaction. We solve for those two in the report sheet. Report sheets, you know, looking at your observations, report sheets can be done in pencil. No problem with that. And so when you fill out your report, do it in pencil. That way, if you make a mistake, you can erase it. Lab notebooks have to be done in pen or ink, you know, because it's supposed to serve as a permanent record. So this has got to be in ink. All right. Any questions about tomorrow's lab? Tomorrow's lab, I'm going to ask you to come prepared because this earthquake drill always screws things up. And I want to finish the whole lab in one day. That way, in the next lab period, we can go to the computer lab, graph all these, and do the calculations. Okay? And so you got to work quickly. You're going to be working in pairs tomorrow. Maybe groups of 3, depending on how many LabQuest systems we have. All right, any questions about this? For tomorrow? Tomorrow, please come prepared. What are the hazards? What's the biggest hazard? Solid sodium hydroxide is a big hazard. You inhale that stuff, it's nasty. You get it in your eyes, you're looking at permanent damage. How do you know if you touch solid sodium hydroxide or sodium hydroxide AQ? It's slippery because your cells are being destroyed, I think, from that. Sodium hydroxide is used to saponify fats. Have you heard of that? Break apart the bonds in fat. People use that to make soaps. So they take fats, mix it with lye, and generate soaps, which are sodium salts of the fatty acids. All right, let's continue on with chapter 7 now. We talked a lot about heat, right? But what about work? We haven't talked much about work, so let's talk about work now. In all these reactions that I just talked about, no work was done. Now, there's different kinds of work. You know, when we look at work, work can be, you know, generating electricity, or it can be mechanical work, like lifting a mass, or it could be generating a sound, you know, these waves. It could be light, generating light. In all of these reactions, did we generate any electricity? Did we lift any masses? Well, you did, but you did the work, not the system. Did we generate any sound? Light? No. Okay, and then the most important type of work is the natural work of a chemical reaction. The natural work of a chemical reaction, well, what is that? What is the natural work of a chemical reaction? The natural work of a chemical reaction is when we do a chemical reaction under constant pressure. Volume changes. Constant pressure, volume changes. For example, potassium chlorate. That reaction you guys did yesterday, that reaction had to do work. The system did work. The system did work because, how did it push all that water out of the flask? Does that require no work? No, that requires work, right? And so producing that oxygen required work. How much work? Well, we can calculate how much work. It's not that difficult to calculate. And so when we do reactions under constant pressure conditions, volumes can change. As the volumes change, then we have the natural work of a chemical reaction. We call it the natural work of a chemical reaction because can you avoid doing that work? Is that work avoidable? No. You could do it in a bomb, right? But if you want to do it under constant pressure, forget it. You got to do the work. And so yesterday's reaction versus all these reactions we're doing tomorrow, all the reactions we're doing tomorrow, no work. Yesterday's reaction, there was work. And so not only did we add heat, right, but we also had work done. Well, where did the energy come from the work? Well, the energy that came from the work came from the surroundings. The surroundings was the burner. And so we had to input a little more energy in there to do that work. Okay, these ones we aren't going to deal with at all in this chapter. The only work we're going to deal with is this. This work is called P delta V work. And so P delta V work. This is P external. And so work is equal to P delta V. The amount of work you have to do in blowing up a balloon is going to be dependent on the external pressure and how big of a balloon you want to blow up. And so that's why it's P delta V. P is normally in atmospheres. Delta V is normally in liters. And so a liter times an atmosphere is energy. And so normally we don't think of liters times atmosphere as being energy, so we got to relate liters atmosphere to joules. So the first thing we're going to do is figure out the relationship between liters atmosphere and joules. It turns out it's easy to figure out the relationship. Liters atmosphere and joules. If you have two things memorized. If you know 0.08206 liters times atmosphere per mole times Kelvin is equal to 8.3145 joules per mole Kelvin. And then what we're going to do is we're just going to divide it. I'm going to divide it this way. I'm going to take 8.3145 joules per mole Kelvin divided by 0.08206 liters times atmosphere per mole Kelvin. Mole Kelvin cancels, and that gives me joules per liter atmosphere. And it comes out to 101.3 joules per liter atmosphere. And so this is how you can understand this. If you blow up a 1 liter balloon in a room that has air at 1 atmosphere, do you know how many joules you just burned through? 101 joules. And so it's going to cost you 101 joules to blow up a 1 liter balloon. Well, what if I went into a 2 atmosphere room? If you went into a 2 atmosphere room and tried to blow up a 1 liter balloon, it would cost you 200 joules. Or what if you were in a 1 atmosphere room and you blew up a 2 liter balloon? It would cost you 200 joules. And so it's very easy to calculate the amount of work depending on the volume expansion. And so if we went from 25 liters to 50 liters, that's 25 liters of volume expansion, we could figure out how much work was done quite easily. And so let's figure out how much work is done if I had a mole of potassium chlorate. If I had 1 mole of potassium chlorate, solid, and this goes to potassium chloride plus 3/2 O2. I think I got the volumes wrong, but this is about 60 milliliters, this is about 40, 50 milliliters. But this is about how many milliliters? This is 75,000 milliliters, no, not 75, 38,000 milliliters, right? 38 liters, roughly. 37.5. We'll be a little bit more precise. So 60 milliliters, about 40 or 50 milliliters, 37,500 milliliters. So what we say are the volumes of the solids are small compared to the volume of gases. And so there are two ways to do these calculations. You do them less precisely. The less precise method of doing these calculations is to ignore solids and liquids and just focus on the gases. And so the volume change was 37,500 milliliters, or 37.5 liters, because it just increased by 1.5 moles, right? That's less precise. The more precise way is if we know, okay, we have 1 mole of this, and I know the molar mass, and I know the density, then I can factor these in and get a more accurate calculation. Both ways are done. Petrucci usually ignores the solids and the liquids, but if you wanted to be more accurate, then you better factor those in, right? Because what we look at is we look at the volume initial and the volume final, and delta V is V final minus V initial. And if we ignore these, then obviously we're introducing error, right? So this is, well, if we go at 37.5 liters, then 37.5 liters, about 1 atmosphere, that's going to give us 3,700 joules, about 3,700 kilojoules of energy that you'd have to input in here to blow it up. Versus if we did this in a bomb, would we have to do the work? If we did this in a bomb, we wouldn't do the work. In this case, delta H and delta U are totally different. Do you see delta H and delta U are totally different because under constant pressure versus constant volume conditions, there's a difference. So the first law of thermodynamics, these calculations are pretty easy if we just know delta V. So we'll look at a more complex calculation next. But the first law of thermodynamics is this: that delta U, the total change in energy, is equal to Q plus W. And then we have this thing about, you know, the sign convention. Do you know the sign convention? If work was done by the system, is it negative or is it positive? It's negative. And so I have to add a sign here. The work of the system is going to equal minus P delta V to make this negative when it blows up the balloon. That means it's going to lose energy in doing that work. And so this is what we have here for this. Okay, so let's look at combustion of methane right now and look at the work involved in the combustion of methane. So I want to figure out what my total energy change is, delta U, total energy change. And so here, if I have methane gas plus 2O2 gas, and I start off with a U initial, let's go at 25 degrees C, and then I go down to CO2 gas and H2O liquid. This is my U final. This is at what? At 25 degrees C. I want to figure out what my delta U is. Well, I can figure out what my delta U is by figuring out what Q is and what W is. In the previous problems, I didn't have to worry about W because we weren't doing any work. You know, we're just doing heat. Potentially, I could have just ignored it too as well. But in this case, we're going to be looking at it. And so let's first figure out how do I calculate W, and then we'll look at how do you calculate Q. But we're out of time, so I'm going to stop here.